Thanks everyone for being here. So I'll talk about the modern way that we measure distances to stars. So this already was mentioned during the quiz. It's the parallax method. And we do that with a spacecraft which is orbiting in the same place where the JWST telescope now is at L2, about 1.5 million kilometers from the Earth. And it's measuring the stars repeatedly, and in that way we can figure out how far they are. And I'll try to give you a very basic idea of the trick that we apply to make this measurement, because as you'll see, there are a couple of complications when you try to apply the parallax method. So the night sky panorama you see in the background was actually made with the Gaia data. So it contains about 1.8 billion stars. Of course, you don't see them all individually. You see the collective light from these stars. But because of this incredibly rich star map, you get this really beautiful view, also very nicely outlining the dust clouds in the Milky Way, etc. Okay, so let's get into it. So what we do to measure distances to stars is we use the parallax method. So basically we're interested in measuring the distance to this particular star over here. And we are observing from Earth, and with Gaia, of course, we're observing from the spacecraft, but let's pretend we're doing this now from Earth. And Earth is in orbit around the Sun, as was discovered by Copernicus. And what we do is we measure the direction to the star with respect to the background stars. And I'll set this animation in motion. So you can see that as we go around on a yearly basis around the Sun, the direction to that star changes on the sky. It describes a little circle or an ellipse, depending on where it is. And that's just a reflection of the fact that we are going around the Sun. Now we put the star a lot further away, and then you can see how the circle that the star describes in the sky becomes a lot smaller. So if we can measure this displacement of the star, which is just a reflection of the fact that we are going around the Sun, we can actually figure out what its distance is. And we can figure out the distance because we know very precisely the distance between the Earth and the Sun, the astronomical unit, which we heard about before, which is about 150 million kilometers. It took a long time to figure out what that distance is, but nowadays it's known very precisely, so we can use it as a standard, together with this top angle here, to figure out how far away the stars are. Now the problem is that trying to measure this top angle of this triangle is very difficult. The closest star to us is about 1 parsec away, a little over 1 parsec, and it means that the circle that it describes in the sky has an angular size of less than 1 arcsecond. And 1 arcsecond, if you take a euro coin and you put it on the other end of Leiden, about 4.5 kilometers away, that's 1 arcsecond. So if you were able to still see that euro coin at that distance. And with Gaia, we're actually doing a factor of 100,000 better in the best cases. So it's an incredibly difficult measurement to make. But I will not go into the technical details as to how we achieve that, but really show you the basics of how you make parallax measurements that are absolute. Some of you may have already noticed that in the way I describe measuring parallax now, there might be some problems. So let's look at that in more detail. So here we have again the orbit of the Earth. We are here in January, here in June, and we try to measure this top angle, the two phases in the orbit of the Earth 6 months apart. But as you can see from this image, measuring the top angle is not so easy because we have no way of telling where the star is. There is nothing in the background. We don't have any reference point to say what is actually the direction to the star. And you need to measure that direction twice in order to figure out this top angle, which is the parallax of the star, and that gives us the distance. So what we need to do is we need to measure the direction to the star, and we need to do that at least twice. And what we do in practice is we say, well, let's take another star, and we use that as a reference. So what we do is we measure this angle between those two stars. That's easily done. That even with telescopes from the 19th century, one can do this very accurately. As long as the stars are fairly close together in the telescope field of view, it's fairly straightforward to measure that angle. Now half a year later, we do the same thing. So we again measure the angle between those two stars. And now you have two angle measurements. Twice you measure the direction of the star that we're interested in with respect to the star that we use as a reference. Now I'll let you puzzle at this over, at home with your knowledge. If you remember about triangles from high school maths. But in principle, the angle that we're interested in is the difference between those two angles. Right? But by the way I phrased my question, of course, the answer is no. The issue is that this angle here is not zero. The star that we use as a reference is not at infinity. And in fact, you can figure this out at home. The difference between these two angles is equal to the difference between the two parallax angles of those two stars. So that's the problem with doing the measurement in this way by using other stars nearby as reference, is that you end up with a parallax measurement that has a systematic error which has to do with the finite distance of your reference star. Now, this method can nevertheless be applied. What they did in practice in the past is said, well, let's choose very faint reference stars, which we can safely assume that they are sufficiently far away that it doesn't matter too much. But if you're going to measure parallaxes at the precision at which we do that in modern times, this becomes a real problem. So what can you do to solve this? And that's the trick that we use with the Gaia spacecraft. Okay, so what we do instead of choosing a nearby reference star, nearby in the sky I mean, is you take a reference star which is located at a very different part of the sky, a very large angle away from the star you're targeting. So now you make a measurement of this angle in, say, January, wait half a year, and you make another measurement of the angle between the stars. And now, again, I'll let you figure this out at home. It's actually true that the difference between the two angles that you measured is exactly equal to the parallax angle of the star. So the trick is essentially that we need to measure parallax by taking a reference star which is very far away from the star that we are actually targeting, very far in angle on the sky. Okay, well, why don't we just do that? It's easy enough. We point to that star, and then we point to that star and just measure the angle. But the trouble is that there is no telescope which can hold in its field of view angles of the order of 90 degrees. You just don't have the optics to achieve that. So the problem is that you are measuring, pointing at the star in this direction of the sky, and then you have to go to, with the same small telescope, to the other star very far away in another direction of the sky, and there's a couple of problems there. One of them is the atmosphere. That's actually the main problem. The atmosphere makes the images of the star wobble a little bit, so it introduces an uncertainty in the direction that you measure. And if the stars are close together on the sky, then the errors that you make due to the atmosphere are more or less the same, so they compensate. But if they are in very different parts of the sky, the turbulence acts very differently in the atmosphere, and that means that you make systematic errors which you cannot compensate for, you don't know. The other thing is that the telescope, if I point it in this direction, my instrument behaves in a certain way. If I point it towards the horizon, my instrument changes orientation, it feels a different effect of gravity, and it deforms a little bit, and that again introduces systematic errors in your measurements. So trying to do this from Earth is basically hopeless. It's been shown before the first of these types of spacecraft was flown, Hipparcos, that maybe you can get of the order of 1,000th of an arc-second precision on parallaxes, and you can hope to do maybe 100 parallaxes a year, and we're doing 2 billion, right? So this is really not possible to do from Earth, that's why they go to space. So this is essentially the basic trick that we use to measure parallaxes. You do it over very large angles, and the way this is done with Gaia is shown in the next image. So this is the Gaia spacecraft, and Gaia in fact carries 2 telescopes on board, so you can see 2 telescope openings. And what we do with Gaia is we essentially measure the directions to the stars in the sky using 2 fields of view that are separated by a very wide angle of about 106 degrees, exactly as I showed in the drawing before. And what we do to make that measurement between the angles between the stars, to make that easy, is that we combine the light from the 2 telescopes onto a single focal plane, onto a single image, so that we go back to the problem of measuring distances, angular distances, between stars over a small field of view, which we know very well how to do. And what Gaia does is it spins around this axis, which is perpendicular to the lines of sight of the 2 telescopes. So every 6 hours it scans a great circle in the sky, And by moving the spin axis over the course of, say, 2 months, we can cover the whole sky. So we change the position of these great circles and in that way cover the whole sky. But the basic trick is to make these angles, or make these measurements over very large angles, and then you can achieve these very high precision parallaxes, and you need to go to space for that. Okay, so that's how we measure parallax with Gaia. I hope this came across a little bit. So let's see what we can do with this. Just one illustration, and I want to make a connection back to the previous talk by Vincent on Huygens. So this is a map, a sky map now of stars in the neighborhood of the sun. I think there's about a couple of thousand stars in here. And they've all been color-coded according to the actual color that we measure for the stars. So we can measure colors of stars as well with Gaia, and that's what you see in here. So what we're going to do now in the next animation is we're going to sort these stars, first according to color, and then according to brightness, and see what we get. So first we sort all the stars by color. We put the blue stars left and the red stars right. And it looks like something rotating, but it's in fact just the shifting left and right of the stars. So everything that's blue will end up on this side of the diagram, everything that's red over here. And now we're ordering them according to their apparent magnitude, how bright they appear on the sky. And as a last step, which we'll just start now, we will also order them according to their distance, according to their luminosity. So we know the distances, so we can actually figure out their absolute luminosities. So we can you know, with the measurement of Sirius, we can figure out indeed that it's 25 times as bright as the sun. I'll let this run again. So first ordering by color. And again, this is now possible because we have for each and every one of these stars a very precise measurement of the distance thanks to this parallax method that I just described. So now we order first by apparent brightness. So this is just ordering by what they would look like on the sky in terms of brightness. And the very last step is where we take into account that we also know the distances to the stars. Now what of course you see is that the stars are not distributed evenly in color and luminosity, but that there's a very distinct distribution of these stars. Now how can we make use of this? And this is in fact what Huygens did. Is we essentially, what Huygens had to do is to assume that Sirius is of the same luminosity as the sun, because there's nothing else that was the best assumption you could make. Now we know that Sirius is not quite the same luminosity, because we have the distance that is measured. But there is also a way to figure out, so you need to know essentially what type of star are you looking at. And there's a way to figure this out. So we have an instrument on board Gaia. Let me see if I can advance. Okay, so Gaia measures these directions to the stars, but we also measure colors, and we do that by having the light fall through two prisms. One prism that measures the light in the blue band, and one prism that measures the light in the red band of the spectrum. And basically, of course, what we do is we make, when the light falls through the prism, you get a little rainbow, and we record the amount of light as a function of the color of the light, and that gives you a so-called spectrum. So we know how bright the star is as a function of wavelength. And this type of data has now been released for the first time from the Gaia mission last year in June. We have spectra like these for about 220 million stars, so the brightest subset of the catalog. And the shape of this spectrum tells us what type of star we're looking at. So if we go back to this diagram is called a color magnitude diagram, or an observational Hertzsprung-Russell diagram. So these stars are very luminous, very bright. These stars are intrinsically very faint. And you need to know what type of star you're looking at, and then you can, from its apparent brightness, you can figure out the distance. This is in fact what Huygens was doing. So here's a star a little bit like Sirius. It's blue, it's luminous, and you can see that it's blue because most of the light comes out in the blue wavelengths. If we look at a star more like our own sun, that tends to be more sort of peaking in the green part of the spectrum. I mean, in fact, to our own eyes, it actually looks white because they're adapted to the sun, but it peaks sort of in the greenish region of the spectrum. And if we go now to one of these very low luminosity stars, so-called M dwarf, then you can see that there's almost no blue light left, and it's all very red light coming out. So by looking at the spectra or looking at the colors of stars, we can actually say something about what type of star it is, and that means, thanks to this calibration that we have here, we know the distances also to a set of stars. So we can actually now make this combination of saying, okay, if the spectrum is like this, then I know the luminosity of the star, and I just go to the sky, measure how bright the star appears to be, and then I know the distance. And this is interesting to do still, because Gaia's parallax measurements have a limitation as to how far out you can go, because at some point parallax stars become so small that even our measurement errors are way too large. But this method still works. So what Huygens did was not only very clever, but still very relevant today. So I'd like to leave it at that. Thanks.
Thanks, Anthony. Great talk. Do we have questions from the audience?
What is the use?
Oh, there was one question in the back. Then I'll come to you.
Yes, thank you. For those stars for which you have a parallax distance and also the measurement of the distance based on the color, do they agree?
Yes, and in particular they agree now because we've calibrated, in fact, this color and luminosity relation, right? There are still certain types of stars for which this is not quite as solid. For example, very rare stars that are intrinsically faint and also difficult to measure by Gaia. There, this kind of calibration is not done super well yet. But for most types of stars, this calibration now tells us, in fact, what the relation is between their colors and their intrinsic luminosity. So yes, they agree.
What is the scientific use of knowing all the distances? What can you do with it?
Well, first of all, the distance tells you more about the intrinsic properties of the star, right? Because we can only tell something about how bright it looks to us. But we don't know whether a star appears faint because it's far away or because it is intrinsically faint, so that's the first basic application. It allows us to make diagrams like this, where we can see that there is a very clear relation between the color that the star has and the intrinsic luminosity. And this, in fact, has helped us understand what the interior of stars look like. What the fact that they're ultimately the fact that there is the burning of hydrogen to helium inside stars, which is what powers their luminosity, comes from these kinds of studies, from noting these relations and, of course, thinking about the physics of it. So this is an excellent diagram to test these kinds of theories, for example. And there's many, many more applications of why you want to know the distance.
Yeah, what we have down here and up there, like this is very bright, this is red dwarfs, and in the other corners we have.
Maybe I go back. Yeah, so these are luminous blue stars. They are typically actually quite young compared to the sun. So these are stars maybe of the order of tens of millions of years old. The sun is of order of 4.5 billion years. Stars down here, red dwarfs, much older, can be up to 10 million years old, but also younger. It's difficult they don't evolve so much in terms of luminosity. These things up here are giant stars, so the sun is sitting somewhere here right now, and eventually it will evolve to become one of those giant stars. So those stars are very much larger and a bit cooler, and because of their enormous size, they're also much more luminous. And conversely, down here are the so-called white dwarfs. These are remnants of stars like the sun. So towards the end of its life, the sun will blow off its outer layers and only the core will remain. And it will stop burning nuclear fuel inside and become very, very small. These things are the size of the Earth, right? And the sun is about 1.5 million kilometers in diameter, so much, much larger than the Earth. But these are the size of the Earth, more or less. And the only thing they do is just cool off over time and become fainter and redder. Back.
Yeah, thank you. So I noticed that Gaia also observes extragalactic objects, and I was wondering what is it observing outside the galaxy, and what does it bring? What discoveries does it make?
Yeah, so Gaia, of course, the majority of things it observes are stars, but in fact it observes anything that looks like a point on the sky. So none of the stars that we observe is resolved by Gaia into a disk. You need a much larger telescope for that. So anything that's point-like will be observed. So this includes, in fact, asteroids in the solar system. So Gaia observes also about 350,000 asteroids in our own solar system, as well as moons of the larger planets and even some objects beyond Pluto. But it also observes extragalactic objects. So these include, for example, stars in the large and small Magellanic Clouds, galaxies orbiting nearby, also stars in the M31 galaxy, the Andromeda Nebula. But Gaia goes all the way out to the distant universe and measures the positions of quasars as well. And the quasars are very important to us because the way we do our astrometric solution is we make this measurement of angles between stars, and this network of angular measurements allows us to figure out the distance and also how the stars move. But the way we do the observations means that if we take the celestial sphere and turn it on its side, there is no effect on the observations. So we don't know what the orientation is of our solution. And likewise, the celestial sphere is also allowed to spin at a constant rate over time. We wouldn't see that in our solution. So we use the quasars on the assumption that they are sufficiently far away that they form a fixed reference frame to fix the orientation and the spin, to set the spin to zero of this celestial reference frame that Gaia provides.
Just a quick follow-up. So did this help you, did Gaia help us in sort of fixing the cosmic's distance ladder? Because I know that there's uncertainties. Parallax can go probably only as far as the Milky Way, but then you have Cepheid variables, and probably you can continue using the Russell diagram, but I'm wondering how much it improves the accuracy of the cosmic ladder.
So Gaia is used to calibrate the Cepheid distance determinations, so looking at the relation between their period and luminosity. And those are then used to calibrate the supernovae, with which you can go even further in distance. And the Gaia, thanks to the Gaia observations, the Hubble constant that we measure locally is now known to within a few percent uncertainty. And it disagrees with the Hubble constant that you get from the cosmic microwave background. So it's made things worse in a way, but also very interesting because these disagreements teach us something new probably about astronomy. Yeah.
Thank you.
Final questions? No, it was a great way to end. Okay, then thank you, Anthony.